Hello students, so continuing our lectures on nanoelectronics, let me first start with the concept that why transistors are used in digital circuits. So, digital circuits, transistors are being used, and the reason of their use in digital circuits is that transistors are two-state device. That means they can act as a switch. And it means you can either set a high or a low value, high or low value to a transistor, which is analogous to the 1 and the 0 in the binary system. Now, apart from that, the second function of a transistor is of an amplifier. So it also amplifies the signal. It amplifies signals transmitted through switches without loss of any strength. The amplification has to be without any loss. Now, the primary transistors used nowadays, or in use today, are called field effect transistors, in which the voltage imposed on the device to control a second output voltage or current. This is given on the device, and it controls the output voltage or the current, or I. Apart from this field effect transistor, there is another transistor called BJT. Stands for bipolar junction transistors. Here, instead of the voltage, we use current to control another current, to control the output current. Now, FET, or the field effect transistor, is a type called Mosfet, or metal oxide field effect transistor. The speciality of a Mosfet is it uses very little power. It is economical to fabricate. and there are three terminals, as in the case of any field effect transistors: the source, the drain, and the gate. Now, usually the current flows between the source and the drain, and the gate, the voltage applied to the gate, it actually controls the current. Now this area which allows the current to flow from the source to the drain is called the channel. And when we are doing the miniaturization for non-electronic devices, so the channel is actually drastically altered. This is where the alteration or scaling down of the device takes place. Now, this whole Mosfet is built upon a crystalline substrate of doped semiconductor silicon. So it can be a p-type silicon or an n-type silicon, because pure silicons are very bad conductors or very poor conductors. So impurities like boron and arsenic are introduced into the silicon to make it a p-type or an n-type. Or it's the opposite, this corresponds to n-type, this corresponds to p-type. No, sorry, p-type and n-type. So this is the valency of the boron is 3 and arsenic is 5. So in the case of p-type there will be extra hole generation, and in case of an n-type there will be extra electron generation. So p-type and n-type impurities. And metal electrode, which is actually the gate, is separated from the semiconductor by an insulating oxide. Separated from the semiconductor by an insulating gate whose voltage and associated electric field controls the flow of current. So it's like the shape as I told you. This is the source, this is the drain, and this is where the gate is. So the gate whose voltage and associated electric field controls the flow of current from source to drain. And that is why divide is called field effect, because there is an effect of electric field controlling the flow of current. So that is the name. FET comes, field effect. Field effect. When the voltage is on, then the gate setter lowers of the voltage, lower of our efficiency, and the region between the source and the drain, we have less negative charges or less negative charges, and this is the reason that less current or low current flows from the source to drain. Whereas when the if we increase the voltage at the gate, just increase the voltage, it attracts electrons to the region under the gate. Attracts electrons to the region under the gate. So this is actually a shape like this. So this is a P-type silicon. We have two different contacts here, N-type. So this is P-type, we have N-type and N-type, and we have the gate at the top of it, and here you have the oxide. So this is the gate, this is the source, and this is the drain. So when the voltage, you are increasing the voltage, what is happening? There are a lot of negative charges are developed just below the gate, whereas the positive charges are here. So this causes the electron to flow from the source to the drain, and there is an increase in current. Now this distinct change in conductivity, that means from a low current to a high current. So this distinct change in conductivity also makes the Mosfet a two-state device or a switch. Two-state device, and also Mosfet can be used as an amplifier. So the two conditions which are required for a device to be used in computers has been attained with the help of a Mosfet. Now, when we are putting a Mosfet inside a chip, or we are scaling down the system, we need to scale down everything. That is how the nanoelectronic devices, the base of nanoelectronic devices, are scaling down. Also, there is very little change in the operation of Mosfet. So this is another advantage, that it can be used in nanoelectronics. However, the problem arises as there is a certain limit, right? So whenever we are reaching 100 nanometer dimension or less, Then, first of all, the cost effectiveness comes into the picture. How, how cost effective it is. These are all the problems associated with it. There are other obstacles, for example, a 40 nanometer. If you are, that has been examples that 40 nanometer size gate length uh, in silicon has been achieved, whereas a 25 nanometer gate length has been achieved with the help of gallium arsenide. So these are all in the research stage. We need to find out whether the dense network uh, of these devices is causing any with the help of flow of electrons, flow of current through extremely narrow wires from one device to another, whether this is causing any effect in the efficiency of the devices. This is still in the research state, and there has been a lot of work going on. There has been a lot of work going on in single electron transistors, resonant diodes and all.